I think this way is better for you and for me too. So I can record the video. Listen up, please. So it's a new subject for you, but not very new. You already know about what the electric charge is from high school, etc. There are two kinds of charges, and the source for the charge is the atomic structure, because we have charged particles in the atoms. The positively charged particles are protons, and the negatively charged particles are electrons. Protons are in the nucleus. The atom is very small. There are two kinds of charges in the nucleus. One is proton, the other is neutron. Neutron has no charge at all, but the masses of the proton and the neutron are almost the same. But of course, since they are very small, the masses are very small, 1.7 times 10 to the minus 28 kilograms in SI unit system. Even for the electron, the mass of the electron is even less than the mass of the proton, but it has the equal amount of charge with that of proton, but in opposite sign. Okay, the electron has a negative charge, and the charge for the electron is 1.6 times 10 to the minus 19 coulomb. Again, it's very small. We are going to work in the SI unit system for the charge as coulomb. And coulomb is the unit for charge. Just like kilogram is the unit for mass, the coulomb is the unit for charge. We use these atomic symbols that probably have seen in... Did you take chemistry course last semester? Yes. In the probably chemistry courses, you have seen this atomic symbol representation. And this part is actually the number of protons plus neutrons. And the lower part, the lower subscript on the left, is the number of protons. From this, you can easily get number of electrons, because the number of electrons and the protons are always the same for a neutral atom. Of course, if the atom is an ion, what is an ion? What is ion? It's charged atom. Charged atoms or molecules are called ions. For ions, the number of protons and electrons are not the same. Okay? Sometimes the number of electrons are larger. In that case, the ion is negatively charged. And if the number of electrons is less than the number of protons, then the ion is said positively charged. So I have given some numbers about the size of an atom. If you bring 6 billion atoms side by side, this makes only 60 centimeters. So 6 billion is the number of total people in Earth right now. So it's that small. It's very small. Okay. And I have shown some demonstration on the electric charge last time, if you were here, that I rubbed some materials, right? The comb to my hair and some bag to my pants, clothes, that you have seen some kind of attraction taking place between the material. And this process is called triboelectric effect. And triboelectric effect, normally all the matter is neutral, okay? The matter there is no extra charge on the matter in everyday life. But if you rub some material onto other, then you will get this charging effect, okay? You will see that after rubbing, for example, the comb to your hair, when you bring some piece of paper to your comb, you will see that a comb will attract these pieces of papers, or as you have seen, the bag will stick to the wall because of these extra charges. This effect is called triboelectric effect. Okay, rubbing the materials and hence by charging them is called the triboelectric effect. And I have tried to show you what kind of material, if you rub onto each other, will get positively charged or negatively charged. If you rub your comb, which is a rubber, hard rubber, into your hair, rubber will get positive or negative charges? Negative, right? And the hair, your hair will get positive charge because the charge is conserved. If some material get an extra charge of, let's say, negative, the other material should get positive, so that when you add them, it will be neutral. Okay. What about the glass, if you rub glass on plastic, and the glass will get positive or negative? Positive. It is positive, and the plastic will get negative. If you do this with silicone and silk, you will get, the silicone will get a negative charge, and the silk will get a positive charge. You have a very nice YouTube video in your modules that about showing this triboelectric series. There are many numbers of different materials, and this actually given in a line. On the top, you will see that the materials will get negatively charged if you rub them with another material which is down to it. Okay, so you will see this, and I, in fact, recommend you to watch this only 5-minute video. Even you can watch from your handy at the bus stop. So one thing that I want to show you that this new kind of property of the matter, which is called charge, induces a new kind of force in the universe. Okay, this force is called electric force. This is unlike the gravitational force that every day you experience from the Earth. Remember, the gravitational force is always attractive. Okay, all matter in the universe attract each other. The planet Earth attracts you on top of it, and two atoms attract each other. Proton and neutron attract each other. Proton and electron attract each other because they have mass. Okay, and we know what this force is. The mass m1 of the first object, the mass m2 of the second object. You multiply them and divide by the distance squared between them. So when you, of course, make the objects far apart from each other, and this force will be less. The similar force between the charged particles is called the electric force, and the electric force is much, much, much larger than the gravitational force. And I will show it to you. As I said, for example, for protons and neutrons, let's say you take one proton and one electron, sorry, not neutron. They will attract each other because they have mass, right? Because of the gravitational force. This we call Fg. And we have learned that they will also attract each other because of the electric charge. Because they have opposite charges, and this is the rule. The opposite charges attract each other, and the like charges repel each other. So since they are opposite charges, they will attract also each other because of the electric force. And I want to show you that the ratio of the magnitude of this electric force between them to the gravitational force is huge number. So let's do it. The electric force, as you already know from the last lecture, we have the charges. The charge for proton is E. By the way, E is always the charge of proton and neutron, and it is a positive quantity, 1.6 times 10 to the minus 19 coulombs, and it is positive. It is minus for electric charge, electron charge, and the plus for the proton. So multiply them, since they have the same charges, and divided by r squared, because if you fix the distance between them r, and you do the same for gravitational force, you write down the gravitational force, the masses, the multiplication of their masses, and divided by r squared. You see, since both type of forces, the electric force and the gravitational force, falls off as 1 over r squared, these r squares will cancel each other on top and bottom, right? So we are left with these E squared and the masses, the multiplication of masses. In addition to that, we have these fundamental constants K and G, capital. K, what is K? It's Coulomb constant, right? It is just a constant determined by experiments, and it's fixed, and it is true for all calculation of all electric forces or between any charges. You have to multiply the charges and with this number. This number is 9 times 10 to the 9. I don't remember the unit, but it's in newtons, meters, squares, and coulombs, whatever. And it is the same it is not the same, it is another constant for the gravitational force, which is capital G, and this number is small. So when you do this, when you put all the numbers, okay, all the numbers in here, and you do this simplification, you will see that this ratio of these two forces is 10 to 40. Can you imagine how huge number is this? Yes. Just add 40 zeros after 1. Okay? You can call 1 million, 10.6, 10 to the power 6 is 1 million. 10 to the power 9 is 1 billion. 10 to the power 12 is
2 trillion.
Trillion. Okay. 10 to the power 15. 10 to the power 18. 10 to the power 20. 10 to the power 30 is 40. You can even not name it. Okay. So it's a very huge number. Anyway. One question for you. For some atoms, not hydrogen, let's take helium. Helium has 2 protons in the nucleus, right? And in a very small region, these 2 protons sit side by side. They don't even, I don't know if they touch each other or not, but they're almost at the same place, right? Because the size of the nucleus is 10 to minus 12 centimeters. It's very small. How can you get 2 protons, which has both positive charges, side by side in a very small region of space? Because they have electric forces, right? And since they are like charges, they repel each other. Electrons have no effect on the forces between protons. Electrons are far away, very far away.
Maybe the gravitational force in them.
No, as you see, the gravitational force is 10 to power minus 40 is less than the electric force. If they attract each other with a force of 1 Newton, then the electric forces, repelling force is 10 to power 40 newtons. So you cannot even compare them. How is that possible? What?
The atom is being empty.
No, I'm talking about the nucleus. Okay, most of the atom is empty because the distance between the first electron in the orbit and the nucleus is huge. If you make the size of the nucleus like the size of an orange, the electron will pass from the orbit is like hundreds of kilometers away from it. Okay, if you enlarge it. So there's no effect of electron on the nucleus. Well, the mass concerns only about the gravitational force between them. As I showed, the gravitational force is much, much less than the electric force. Have you ever heard about the nuclear force?
Yeah.
So in the universe, there are 4 different kinds of forces. Okay, one you have already seen from last semester, the gravitational force. Okay, and this will affect all the universe because there are lots of astronomical objects in the universe, so they all attract each other. Like galaxies, the formation of galaxies, the sun systems, etc., is because of the gravitational force. And the second one is the electric force that you already seen the last lecture, is because of the charge. The other 2 forces are called the nuclear forces. They only exist in nucleus. Okay, they don't even exist if you are away from the nucleus, okay? Because they are very short-range forces, and they will only affect, will be observed only in the size of the nucleus. And if you are out of the size of the nucleus, there is no effect of nuclear forces. So there is a kind of nuclear force between the protons. It is also exists between the proton and the neutron. Even the neutron is chargeless, because the nuclear force does not count the charge. It does not depend on the charge. There is kind of a force between these nuclear particles. This force holds even much, much larger than the electrical force inside the nucleus. That's why 2 protons, 3 protons, more protons are can be held on the nucleus side by side. So this is all right. So let me talk about this superposition principle of electric forces that we already know. If you bring 2 charges, they will attract or repel each other. And we know what the force is between them. It's just 1 over r square. It depends on 1 over r square, inverse of the distance, and depends on the charge. If we have 3 charges, okay, and you want to find the force on the 3rd charge, you have 3 charges in the picture you see. You already bring these 2 charges, Q1 and Q2, and you bring the 3rd charge on here, okay, which has a distance between the Q2 and Q3 is A, and also Q1 and Q3 has a distance between them A. So these corners are the squares of a corner, and we put a coordinate system y and x, and the charges are given here. Q1 and Q2 are given. Q1 is positively charged, 6 times 10 to the minus 6 coulombs, and Q2 is negative of it, and Q3 is half of this charge, and the distance between them, A, is given. If these are on the corner of a square, what is the distance between Q1 and Q3? Square root 2A. Okay. So let's try to calculate the total net force on charge Q3. We know Q2 will repel or attract Q3? Repel. It will repel. No, it will attract. Okay. Let me show it. So you see, this is the force on Q3 because of Q2, because Q2 is a negative charge. And this one is the force on Q3 because of Q1, because it repels it. But the distance between Q1 and Q3 is not equal to A, but it's square root 2A. So we will calculate these 2 forces, and we will add these 2 forces with the rules of addition of vectors, because the forces are vectors. Let me denote this F13 as the force on the charge 1 on Q3, and F23 is the force on Q3 by Q2, and the sum is just the vectorial sum of the forces. So vectorially we have to add them. All electrical forces depends on the charges. The first one Q1, Q3, and the other one is Q2, Q3. And distance squared. The distance squares, R13 is the distance between 1 and 3, charge 1 and 3. And it is this one, which is, if you take the square, it's 2A squared, right? Because in square root 2 times A. Let's do all this. But you have to be careful in adding these 2 vectors, because you have to provide the unit vectors. These are the unit vectors. R hat 13 is the unit vector in this direction, right? And this unit vector, in terms of the unit vectors in x and y, is given by this. Okay? Because it has both the projection onto the x-axis and on the y-axis, so it must be written as the sum of I and j. So what is the coefficients? It will be equal amount of coefficients, because the angle is 45 degrees. It is the same 45 degrees with the y-axis. So it is cosine 45 I plus sine 45. So this is the unit vector between Q1 and Q3, showing the direction of F13, and it's 1 over square root 2 I plus j. You know what I and j are, right? From the last semester. They are the unit vectors in x and y. So you have to also determine the unit vector in this direction, is R23, and it is, since in the direction of positive x-axis, it's just I. That's it. Because we can carry the unit vectors anywhere on the coordinate system. No problem. So you do all the calculations and you put the values. We add vectors as vectors. You have to add i's and i's together and j's and j's, because there is no j in R2, 3, so you just add this I, coefficient of I, in here, okay? So when you do this and put the numbers, everything, you will have F3, the net force on Q3 is 3 newtons, okay? The next question, what is the direction of F3? Whenever you see a question in your quizzes and the exams about the direction of a force, you have to calculate an angle, okay? Whenever you are asked the direction of a force, you have to calculate the angle, you see this angle, of F3 to the x-axis, okay? Remember, the angles for the directions are always measured from the x-axis, okay? You have to measure the angles from the x-axis. So what is this angle? And it's very easy. Again, it is just the arctangent or inverse tangent of the vector component y, right? F3y divided by its x component. When you do this in your calculator and plug and check, you will obtain 151.3 degrees. So this is enough for you to write down the direction of the force F3. Any questions? So if you had more than 3 charges, 4 charges, 5 charges, if you bring more charges around, you do the same. One by one, you will calculate the force on each charge on Q3 and add them vectorially. That's it. This is called the superposition rule, okay? The next very important subject in the first chapter is the electric field, okay? What is electric field? And this is something new for you because you haven't seen anything such in first semester. Imagine we have a charge and plus charge Q on one location in space. And you bring another charge to a point P in the space, okay? And, well, you can easily say that this new charge will experience a force because of the larger charge, right? And this force is just Q times capital Q times small q divided by the distance square, right? Here. Okay. Wait. So I define the electric field at point P created by this capital charge Q as the force on point P divided by this test charge Q. We call this small q as the test charge. You can even make this test charge as 1 coulomb. Okay, this is because of the test charge. When you divide this force by the test charge, the quantity that you find or you define is the electric field created by the capital charge Q on the point P. Okay, this is just the definition. Well, what is the exact formulation? If you write down F, the force, explicitly in terms of the charges and the distance between them, K, capital Q, small q divided by R square, and divide by small q, you get K, the charge Q, capital Q, divided by R square. And of course, you have a unit vector, R. So as you see, the electric field at point P created by this charge Q only depends on the charge itself, Q, and the distance between the point and the charge Q. Okay? So it is given by this formula. Electric field is just like a force. Electric force is a vector. Okay? Electric field is a vector. And one thing about the electric field, if you imagine one point charge in space, let's make this charge as positive, okay? Put in here. At every point around this charge, you can define the electric field, right? In close points, like in this point, which is very close to the charge, since R is small, the electric field will be large, right? So you can just draw a arrow line showing the electric field at that point. But if you go away to a larger distance, like imagine this point, the electric field at that point, again it will be the same direction, but it will be less because the distance is large. So if you draw another line, it will be shorter. You do the same in every direction, right? In every direction around this point charge, you can define the electric field. There is an easier way to show these electric fields, okay? This is the case if you have a negative charge. The directions in that case, since for the negative charge Q is negative, the directions of the arrows will be toward the charge, inward, because the directions are reversed for a negative charge. And the electric field depends on the sign of the charge, because it depends on the charge, right? Instead of drawing arrowed lines at every point around this charge, let's do this. We just do the following. Let me connect all these electric field vectors in here. Okay, I'm just connecting these electric field vectors. Okay, here, this one, this, and this. So now you see only lines, okay? And these lines are called electric field lines, okay? And the electric field lines, as you see, when you look at, they are denser, they are closer to each other, these lines are closer to each other when you come close to the charge, right? But when you go away from the charge, these lines are now separated. They are far away from each other. So I can say this: if you want to know the strength of the electric field vectors in one region of space, when you look at that region, when you look at the electric field lines, if the electric field lines are far from each other, then the strength of the electric field at these regions are small. Just like the case around here, these spaces, okay? Because electric field lines are getting away from each other when you go away from the charge, because you're increasing the distance. These field lines are away from each other, and the electric field vector is less in these regions. But when you come close, electric field lines are closer to each other. That shows the electric field vector in these regions are large. So electric field vectors and electric field lines are not the same, but just by looking at the field lines, you can figure out the strength of the electric field, okay? And in fact, when we are examining the conductors, the metals inside some electric fields, you will see how these electric field lines are emerging, not from point charges, but from the metal surfaces by using this fact. Okay, just like electric field force, we can superpose the electric field vectors, okay? So if you have two charges, one is, let's say, Q1 positively charged, the other is negatively charged, and you want to find the electric field vector at this point P, okay? What you do? You just calculate the electric field vector for the first charge Q1 and the electric field vector for the other charge. Well, for the first charge Q1, the electric field at this point is away because the charge Q1 is plus. And for Q2, the electric field at this point is toward Q2 because it is negatively charged, right? The directions of the electric field lines depends on the sign of the charge. And what to do next is, since they are vectors, again, just add them by vectorially, just making a parallelogram, and the resultant electric field, because of these two charges at point P, is just a vectorial sum, right? If you have n charges, n point charges in scattered around a region of space, and if you want to find the electric field at one fixed point, what you do is you sum the electric field vectors for each charge at that point. That's it. And this will be the resultant electric field. You can have as many charges as you want. The thing to do is just add them vectorially. Okay, this is just I have showed in the previous picture, right? I have shown these electric field lines. And you will see that on the electric field lines, these arrows only shows the direction of the electric field at these points, right? On one line, the electric field is always in the same direction. It is enough to put only one arrow on one line. That's it, because at everywhere, the direction will be the same. All right. Well, this is the electric field line distribution for only one charge. But what about the electric field line distribution if you have two charges which are separated by some distance? How to do this? At some points in space, just pick up some points. Let's choose this one. The electric field at this point, because of small charge, minus Q, let's say, is this one. And at the same point, electric field, because of the plus charge, Q, is this one. Because it's closer to plus Q, so it will be larger than the minus one. So the resultant is just the addition of these two vectors, which are parallel to each other. Just erase them and put one line or one vector. You do the same at any other point. You just calculate the electric field vectors and add them. What about this point? What do you think the direction of the electric field line or electric field vector at this point? So because of the plus charge, the direction is like this. It is always away from the plus charge. And because of the minus charge, it will be like this, because it will be toward the minus charge, okay? Imagine this is connected by a line, and the electric field vector from the minus Q should be parallel or on top of this line. So this is two vectors, and you have to add them. That's the result. You do the same in here. If you add them, because just in the middle, but in top, this, but you get the idea, right? And just imagine there are always two vectors and connect them, okay? You connect them, erase these arrows now. You see now two lines, electric field lines between the two charges, okay? You always show the direction. So another line, this part in the region should be symmetric to this one, right? It is symmetric. Just draw a symmetric one, a mirror symmetric one. And as you go away, you will see that these lines will curve toward they will emerge from plus, and they will end up on the minus. So when you do this, you will see that some of the lines, electric field lines, will be emerged from the positive charge, and they will end up on the negative charge. But you see, some of them are not, right, emerging and ending on the other part. They are just going to the infinity, all right? You don't have to, bring all the lines on top of each other, because this line has no way to curve from this side or this side to come to the minus charge, okay? So this specific charge distribution, on one side you have plus Q, and on the other side you have minus Q, but their magnitudes are the same. This specific charge is called dipole. This is called dipole because you have two charges. Di means two in Latin, okay? And the dipoles are the very important charge distributions that you will face all of your electronics engineering classes, almost. This is one of the most important charge distributions in your engineering life, dipoles. You will see dipole antennas, dipole emitters, many things about dipoles. So you have to learn these dipoles very well. So there's a better picture of a dipole. You see here, there are many lines. When you have such a distribution of electric field lines in space around point charges, how to read this? Okay. When you look at some region of space around these charges, if the lines are closer to each other, okay, this region of space has larger electric field. Okay, electric field, for example, here, and just right around these charges are the most largest part in the space. When you go away, you see the electric field lines are getting away from them. So they are scattered now, and they are less dense. That means the electric field vector is small. The resultant electric field vectors are small in these regions. Well, this is for equal amount of charges, but they are opposite, as you see. We always show the red ones are plus charges and blue ones are minus charges. But what if you have unequal charges? One of them is not in strength equal to each other. Suppose you have these two charges, okay, and they are both positive, right? And you see how the electric field lines are on, right? The electric field lines, you see, you never see any electric field line emerging one, let's say from the left one, and ending on the other one. This is not the case if the charges are equal sign. If they have the equal sign, this is also the case. For example, this is for plus, this is for minus. You never see any line emerging from one of them, ending on the other. This is not the case if the charges are the same. And you see there is some region in around this. Concentrate on this region. Can you say some point in here the electric field should be zero? Is there any region of space, any point for this charge distribution that at least on this region, not infinity, but on this region, can you say at any point the electric field should be zero? What about this? Well, first of all, you see these charges are not equal strength, because on the left charge you see 1, 2, 3, 4, 5, 6 lines emerging. And if you count the right charge, there are 18 lines, if you count. 18 lines emerging from the right charge. This shows that 3 times larger number of, 3 times more number of lines, electric field lines emerging from the right charge. That means if this charge is Q, plus Q, this one is 3Q, because there are the number of lines are 3 times larger than the other one. So you can compare just by counting the number of lines emerging from each other. Well, when you look at closely to this picture, okay, if you look somewhere here, like here, this point. At this point, what is the electric field? Because of the left charge. It is in this direction, right? At the same point, what is the electric field because of the right charge? It is in the opposite direction, right? And so there is a possibility that these two lines, electric field vectors, cancel each other. This point will be closer to the less charge because the charge has a less strength than the other one. So it will be closer, not right in the middle, but it is a point closer to the less charge that the electric field is 0. So there are points, there might be some points on, if you have more number of charges in the space, there might be some points that the electric field, net electric field is 0. Okay, so for example, this one, it's not a dipole because, well, they have opposite charges, that's must for a dipole, but their strength are not equal to each other. The minus charge, if you see in magnitude, has a larger charge because it has more number of field lines coming into it than the left charge. So it's an unequal amount of charges, the distribution you see. Then the electric field lines are not symmetrically distributed around these charges. So this is another possibility. But if you look at, let me ask a question. Let's make this Q, okay, this is plus Q, and let's make this, let's minus 3Q, whatever. Sorry. If you look these 2 point charges very, very, very far away, if you go very far distance, and when you look at these 2 charges, what do you see as a net charge? From a far distance, you will see the net charge as minus Q, right? Because if you add these 2 charges, one is plus Q, the other is minus 3Q, the total net charge is minus 2Q. If you go very far away from these charges, you will see an electric field line distribution just like you have a 1 point charge which has a minus 2Q. Okay? So this is what it looks from far away. Let me give a break and then we will continue. Let's after 10 minutes, okay?